Okay. And now that picture's frozen, so struggling today. There we go. Okay. This unit up until now has been integration. Integral, 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 integral. So what makes today different? Derivatives. Okay, but don't read the rest of it. Generally speaking, you'd rather derivatives than integrals, right? Because derivatives are more straightforward. Integrals is use substitution and work backwards and be careful with the du dx thing and then change the limits. And so we don't have to worry about any of that today. But why are you grimacing when you look at what we're doing today? Well, it's not the derivative part, maybe. It's the inverse trig functions. So what we're going to do, we're going to start out with reminding ourselves about inverse trig functions. So not even derivatives yet. Let's back up a little bit and talk about inverse trig functions. Try the first three. Do I need to go over the first one? Okay. Okay. So do you remember what that means? Inverse sine of 1/2. So what's the question you're asking yourself?
1 over that. 1 over sine.
It's not 1 over sine.
Cosine.
No, well, way off. Inverse sine is, this means, this means find an angle whose sine is, that's what inverse sine means. So that means find an angle whose sine is 1/2. So that -1 does not mean flip it over. That's what you're thinking. If you flip sine, you get cosecant. But that's not what that -1 means. It means go backwards as you're pondering the unit circle. And where is the sine equal to 1/2? Pi over 6. So the answer is pi over 6, because the sine of pi over 6 is 1/2. Okay, that is what we're going to talk about in a minute. Because, so Ben's question was, well, why isn't it not also 5 pi over 6? Because clearly the sine of 5 pi over 6 is also 1/2. But inverse sines can only have one answer, because they are functions. So you can only have one output, right? It wouldn't make sense to have two outputs. You only get one answer. And so you have to pick the best angle, and that's the trick that we'll talk about in a minute. So find the best angle, the easiest angle, whose sine is 1/2, or whose cosine is 1/2, or whose tangent is root 3 over 3. So try 2 and 3. The tangent of pi over 3 is, anybody remember? Root 3. Right? It's the tangent 3 trick. Like pi over 3 gives 1 3. Pi over 6 gives you 2 3s. One silly way to remember it. Easy way to remember it. Okay, let's flip this over and talk a little more in depth, because Ben was onto something there with that, wait a minute, isn't there more than one answer thing? Inverse trig functions. Because they are functions, have only one answer. And so it's not enough to know the unit circle. That's part of it. But you also have to know, well, which angle on the unit circle should I use? And you have to know the restrictions. So I'm going to write the restrictions, and I'm going to give you the shortcut for remembering the restrictions. Meaning, if we're doing inverse sine, we have to pick an angle from quadrant 1 or quadrant 4. because we need to pick up some that are positive and some that are negative. So 1 and 4 would do that. For cosine, we're always going to be using quadrant 1 for any of these. Where is the cosine negative? So where can I get some negative values? Which quadrant? 2. Or 3, but if I want the easiest answers, I should probably stick to 1 and 2. And then tangent's kind of tricky because quadrant 1's still positive. Where is tangent? What quadrants have a negative tangent? 2 and 4. So it's like, well, that means you could argue that it should match sine because you would get positive and negative. You could argue it would match cosine to get positive and negative. Do you know where the asymptotes for tangent are? Let's see, tangent is sine over cosine. Cosine would have an asymptote, or cosine would be 0 there and there. So we'd like to avoid hitting that asymptote. So to avoid crossing the asymptote, we'll pick 1 and 4. That's kind of the hard one. Like sine and cosine, you're probably going to get right just because if you pick the easiest angle, you're going to naturally pick something from 1 and 4 or 1 and 2. If you want inverse tangent of negative, then you have to be a little more careful. You have to pick something from quadrant 4. Okay, the shortcut is stay out of quadrant 3. You'll never use quadrant 3. Never go there, and never go through there. Never go to quadrant 3, because you don't have to, but also never go through there. That means if you want to pick something from quadrant 4, you have to get there the short way. So negative angles. You can have negative angles for an answer. Stay out of quadrant 3. So that's kind of the short answer. If you stay out of quadrant 3, you're going to get most of them right. That's about the only rule you need. The only trick is inverse tangent of a negative number. You have to know to go to quadrant 4 rather than quadrant 2. So sine and tangent, quadrants 1 and 4. Cosine, you pull from quadrant 1 or 2. Okay. Flip that back over and try those next 6. You hit some negative ones in a moment. Arc cosine, that means the same thing as inverse cosine. All right, so you try 4 through 9. Yeah, same thing as the number 7. You can't go the long way around. You have to give the shortest answer. As long as you give the shortest best answer, you're going to get it right. All right? You don't really have to remember the restrictions. As long as you give the shortest best, or the shortest answer, the shortest way to get there, you'll be okay. All right, ladies, back on here. So that's all inverse trig. That was no calculus in any of that. That was all just a review of pre-calc. But we're going to need that because in a moment, like right now we're going to do derivatives of inverse trig functions. So now that you're, again, experts on inverse trig functions, let's grab the notes packet, and we're going to do derivatives of inverse trig functions. Okay, some people like this lesson because it's a little different. Consider y equals arctan of x. So that means y is the answer to find me an angle whose tangent is x. So another way to say that is that x is the tangent of y. I guess another way to do that would be like take the tangent of both sides, and tan and arctan would cancel each other out. and so the tangent of y equals x. Okay, so let's see if we can draw a picture that shows the tangent of y being x. Okay, well, if we're taking the tangent of something, that something has to be the angle. So let's put our angle right there. Let's see, tangent of y equals x. What's the letters we usually associate with tangent? I don't know if you know what I'm even asking there. Sine over cosine, that's true. O over a, that's one way to say it. It is y over x. Be careful with that because we've already are using y and x, so let's don't use that. Let's just go back to old school SOHCAHTOA. So opposite over adjacent. How do I make just x match up to opposite over adjacent? You remember doing this? You've done stuff like this a while back. What could I put under x to make it? Let's just put it over 1. Making things more complicated. X over 1, that's the same thing as x. And then we can match up that x is the opposite side and 1 is the adjacent side. Okay. Let's back up a second. What we're trying to find on all these is dy dx. So let's take the derivative of both sides. So d dx of tangent of y equals d dx of x. Okay, what's the derivative of tangent? The derivative of tangent? Secant? Secant squared of y. But that's not enough. Not plus c, that would be inverse derivatives. Times dy dx. Maybe we should have done the other side first. What's the derivative of x? 1. So that means that dy dx, which is what we're trying to find here, is equal to 1 over secant squared of y. Okay, there's a better way to say that though. What's 1 over secant? 1 over secant is cosine. So dy dx is cosine squared of y. Dy dx is cosine squared of y. But, well, back up. So that means that's the same thing as the cosine of y squared. But what's cosine? Back to SOHCAHTOA land. SOHCAHTOA, adjacent over hypotenuse. So let's figure out what adjacent over hypotenuse is, and then we'll square it. So let's see. Adjacent is 1. That's easy. Hypotenuse. Oh, that one's not as easy. We can use a squared plus b squared equals c squared to get the hypotenuse. So that'd be the square root of x squared plus 1. Right? A squared plus b squared equals c squared. So square root of x squared plus 1. Oh, well, this works out kind of nice for us. Because what happens when we square 1? We get 1. And what happens when we square the square root of x squared plus 1? Yeah, the square root and square cancel each other out. So all that to say, dy dx is 1 over x squared plus 1. but y was the arctangent, back all the way to the beginning here. So this means the derivative of arctangent, the derivative of y, is 1 over x squared plus 1. Okay, the good news is, I guess this is good news, probably good news to most, you don't have to know the process. You just have to know the answer. So you can, if you didn't like any of that, you can ignore all that, but you do have to know the derivative of arctangent is 1 over x squared plus 1. What's that? Memorize that.
Will the reading questions on like the test will have to do something similar to that?
No. Will you have to like derive it? No.
Yes.
Or come up with it on your own? No.
Then what's the...
So that was for your own academic and intellectual enjoyment, Jace. Right? Now, given Jace's and maybe everyone else's taste or distaste for that academic and intellectual enjoyment, would you like me to go through the whole process for arcsine, or would you just like the answer? That's what I thought. It follows the same process, but we don't really need to worry about it. The answer is 1 over the square root of 1 minus x squared. But you could get there going the same route. But you don't need to. That's right. Just know the answer. It kind of looks like somebody used a squared plus b squared equals c squared, so maybe that makes sense. Again, I could go through the whole process, but no. And then arcsecant, again, same thing. You could draw a triangle. You could do a squared plus b squared equals c squared. But in the end, you get 1 over the absolute value of x times the square root of x squared minus 1. Okay, so that's 3 new derivatives that we have to know for today. Okay, well, it's 6, but these, as you know, these are all related to each other. So here's the big table that you have to know. Arctan, we just did that one. That's the easy one. 1 over x squared plus 1. I feel like it's rare that tangent is the easiest of the bunch. 1 over x squared plus 1. Any guesses on what derivative of arc cotangent is? It's really similar. Okay, that's not a bad guess. Ben's over there like, flip it, because tangent and cotangent are flipped. They are flipped, but it's just the negative. And you don't even have to flip it. So it's negative 1 over x squared plus 1. Let's see, arc sine, that's 1 over square root 1 minus x squared. Derivative of arc cosine is just change the positive negative, so make it negative. And derivative of arc secant, that's the craziest the craziest derivative, but that makes sense. Secant seems like it would be crazier than those. Absolute value of x, square root of x squared minus 1. And then cosecant is just the negative version. Okay, so there's the main 3. You can just get the other 3 if you need them. How to memorize those? I've not come up with any catchy phrase or anything to help on this. Tangent's the easiest one. Because it's adding, if you get the denominator backwards, it doesn't really matter, right? Because x squared plus 1, 1 plus x squared, same thing. sine and secant, the order matters because you're subtracting, but you've got to remember which one goes where. And for sine, it's 1 minus x squared. For secant, it's x squared minus 1. I don't know that there's a... Yeah, all the co's are negative. That's the easy part. But keeping these straight is the trick. And usually people are good on tangent because it's the easiest one. And because if you get the denominator backwards, it's not really backwards because you're adding. So that one's fine. It's the next two that are... People get the what's in the radical backwards. That's what messes people up. Because one's 1 minus x squared, the other's x squared minus 1. So however you can remember which one goes with which, that's the tricky part of those. Like the absolute value of x, that makes it extra tricky, but people remember that that's just part of secant, so nobody messes that up. It's only usually the square root thing that people get backwards. Okay, so let's try to use those. Number one, if f of x is the arc sine of x squared, then f prime of x, okay, so I'm looking at arc sine. The derivative would be 1 over square root 1 minus the argument squared. So this one's a little different because there's an x squared in there rather than an x. So square the argument, and we'll fix that in a minute. Well, what else do you think we need to tag on to the end of this? 2x, because that's our blow-pop rule, our chain rule. So times 2x. That would be a safe stop. If you wanted to clean it up a little bit, it might look like that. Number 2, arc secant. So I'm looking at my arc secant formula. The 3 is out front, so I'm not really worried about the 3. The 3 can just come out front. 1 over absolute value of the argument. So 2x square root the argument squared minus 1. And why am I not done with that? Chain rule. So what do I get on the end of that? Times 2. Okay, again, that's a safe stop. But it's probably not the multiple choice answer. I can reduce the 2's. Be careful with the absolute value, but the 2 is not going to change any signs. So I can reduce the 2's and get 3 over absolute value of x square root of 4x squared minus 1. Again, right now you don't have these memorized yet, so that's okay. We're just looking at the formula and plugging things in. Why don't you try number 3? It might be helpful to rewrite. What's another way to say the square root of x? X to the 1/2. So look at the arctan definition. There's our argument. And don't forget the chain rule. So try. First part is nice. You end up squaring x to the 1/2. That's the easy part. Chain rule. Now you've got to remember the derivative of x to the 1/2. So that's 1/2 x to the negative 1/2. That would be a safe stop, but no multiple choice answer is going to look like that. So let's see if we can clean that up a little bit. Squared the square root, that cancels each other out. 2, and then that's the square root of x. So, still not quite the cleanest way to write that. That's probably what the multiple choice answer would look like.
Wait, how did you get X?
How'd I get
How'd that turn?
this? Because I squared the square root of x?
Because of multiple. What do I do?
What are you going to have to do on number 4? How are those two things connected there? X times arctan x. So, what rule is that going to? Product rule. So, try number 4, but definitely use the product rule. So,
Mallory's brain, but she was
I don't remember who did what order we should do it in. It doesn't matter. First times derivative of the second plus the other way around. So the derivative of the first one times the second. And obviously that could be cleaned up a little bit, but not really. Like, I don't need the 1, and I could put the x in the top, but that's minor. Number 5, write an equation of a tangent line to the graph of this thing at the point. So what two things do I need if I want to write the equation of a tangent line? A point and a slope. So they gave me the point, that was kind of them. And the slope would be the derivative. So I'm going to have to find the derivative of 2 arcsecant 3x. So look back up at my answer here, my formula chart. So 2 over absolute value of the argument times the square root of the argument squared minus 1. Times 3. Why times 3? Chain rule. Now that is y prime, but I don't really want y prime. I want y prime at x equals 2/3. So now I need to plug 2/3 in everywhere. Yeah, I'm thinking, do I want to reduce the 3's or do I not want to reduce the 3's? Because I'm about to plug in 2/3. So it might be easier if I leave that 3 there, because 3 times 2/3 makes my life easier. That's just 2. So yes, I can reduce those 3's, and yes, I could make this 9x squared, but since I'm plugging in 2/3, it might be better to just leave it as is, and then plug in the 2/3. So 6 over 3 times 2/3, square root of 3 times 2/3 squared minus 1. And I suppose if you were interested or not interested in cleaning that up, you could use that whole chunk of stuff and write that as your slope when it comes to y minus y1 equals m times x minus x1. You can do that. You can kind of cheat your way around it here. You can say, you know what, I don't want to simplify it, and I don't want to rewrite it, so let's just call it m, and then write m right there. And there we go. You are allowed to do that on free response questions. You are encouraged to do that. If you get a weird answer that you're going to need later, don't write out 14 decimals, or don't write out something crazy. Call it A or B or C or M, if that makes more sense for this one, and then you can just use M the rest of the way. That's going to start happening more and more we get crazy answers that we need later. You're like, I don't want to write this a bunch of times. So call it M, and you don't have to rewrite it. Now, on a multiple choice test, we'd have to clean that up. So let's do a quick check on our algebra skills here. 2 square root of 4 minus 1 is 3. And again, that's a safe stop. But that's 3 over root 3, which is just root 3. So depending on how much algebra you want to do, you could get it down to square root of 3. But on a free response question, you should do exactly what Addie said. Label it M, use the M, be done. Don't mess up the algebra. Number 6. What is the slope of the line tangent to the graph? So that's fancy talk. Avery, what are we at? What are we looking for here? A derivative. Fancy talk for derivatives. Given by, ooh, yuck, arc tan x plus y equals arc sine x plus y at the point 0, 0. Well, at least we're plugging in zeros, so that should make things a little bit easier, I guess. So, probably want to slow this one down a little bit. So let's take the derivative of both sides. I think this is going to get ugly, but all those zeros in there should help us out. Okay, I guess one side at a time. Derivative of arctan, that's not too bad. That's 1 over, be careful, our formula says x squared, but what we really mean is argument squared. So what am I squaring right there? xy. But I'm not done. What else do I need to do? Well, sort of. I need to think about the chain rule, so I need to take the derivative of x times y. Well, that's going to be a product rule. So x times dy dx, or y prime, plus 1 times y. Yuck. Okay, on the other side, arc sine. My argument is x plus y, so I'm looking up at my formula chart. So it's 1 over square root 1 minus argument squared. So x plus y goes in there. Chain rule times the derivative of the argument. So what's the derivative of x plus y? It's an easier one.
1 plus y prime.
1 plus y prime. Derivative of x is 1. Derivative of y is y prime. Okay. And I'm trying to solve now. I want to know what y prime is. So I could do some awful algebra first. But what would make my life easier than doing algebra and moving things around? Let's plug in 0, 0. That's going to wipe out a whole bunch of stuff. So 1 over 0 times 0 squared plus 1 is 1. 0 times y prime plus 1 times 0. That's really nice. What does the whole left-hand side of my equation become now? Careful. 0 plus 0 times 1 is 0. On the other side, 1 over square root 1 minus 0 squared times 1 plus y prime. So all of that's 1. So our derivative was really ugly, but the algebra was really easy. So y prime equals negative 1. I need the opposite stamp for that problem. The calculus was hard and the algebra was easy.
Why did the whole second? So why did that go? What was the slope of the line?
Because 1 minus 0 is 1, and the square root of 1 is 1, and 1 divided by 1 is 1. And so 1 times this stuff didn't really matter. All of that's 1. Well, yeah, that's the ugly one. You get some of those right, you start making 4s and 5s on the AP test. All right, today's assignment is worksheet 5. I wonder if it would be wise, so get out the worksheet. And at the very top, let's rewrite the 3 main equations here. And they won't all fit, but that's okay. I know you have them elsewhere, but it helps your brain remember it just by writing them down and by saying them. So even though all you're going to do is read off the page, I'm going to ask you to read them out loud to me. Because again, every time you say it or write it, it helps get in your brain. So Abby, what's the derivative of the arctangent of x? Good. Again, I know you don't have them memorized yet, and so I know you're just looking at this formula chart, which is fine. Ambria, what's the derivative of the arcsine of x?
1 over square root 1 minus x squared.
Good. And Bailey, what's the derivative of arcsecant?
1 over absolute value of x times square root x squared minus 1.
Good. Again, 2 purposes for writing them there when you don't really need to, right? One is to have them more convenient while you're working the worksheet, but the second reason is physically writing them down helps them stick in your brain. So try 1 and 2. Try 1 and 2. We'll see how we're doing on this. Some of you sort of emphasize that, hey, I remembered the chain rule. Look at me times 1. Not necessary, but nothing wrong with it. Secant, that one's kind of a pain because it's got the absolute value. Square root of 25x squared minus 1. Some of you stopped there and earned yourself a blow pop. Not because you got it right, but because you got it wrong. Proudly so over there. Chain rule times 5. Number 3 has a definite chain rule situation waiting to happen.
I thought you said 1 and 2.
I did, but eventually you got to do them all, so why don't you go ahead and try 3. Resume. Yes, I left off the 2. That's not a blow pop mistake, but it is a mistake. All right, try 3 and 4. Okay, number 4. Let's see, that would be quotient rule. Although, hold on, give me a couple minutes here, then we'll be done. Ben, did you do the thing that you asked about, or did you stick with quotient rule? Okay. Do you know how to get out of doing quotient rule? If you really, you can make it x to the negative 1 and then do product rule. But the derivative of x to the negative 1 is a little harder than the derivative of x, so trade-off. I'm going to do it as quotient rule because I think that's probably what most of you did, but you can always avoid the quotient rule by taking whatever the denominator is, moving it to the top with a negative exponent. So it's always avoidable, it's just which would you prefer? Okay, so GF prime. So the bottom times the derivative of the top. So 3x squared plus 1, chain rule times 3, minus the other way around, top times derivative of the bottom. So that's kind of easy, since the derivative of x is 1, over x squared, and it's a free response question, and the algebra would be ugly, so box it up and be done.
Where? Oh, wait. I have it over here. Oh, you put it
Are you okay with that? Did you put the 3 somewhere else? Okay, peeking ahead, tomorrow we will do integrals yielding inverse trig functions. So tomorrow we'll take what we learned today and put it in reverse and go backwards. So that means you have to know them pretty well. Like, look at number 1. This should be fresh on our mind. Do you remember? Like, you don't know the details yet, but do you know which trig function this is headed toward? Arc sine. Do you remember what this one's headed toward? Like, you can get these.
The same one.
Yep, arc sine. How about number 3?
Or secant. See cosine. Sine.
Still arc sine. What about number 5? Arctan.
Mallory got it.
Because it looks like an arctan. Some of the others will require some U substitution to get there. But we'll save that for tomorrow. All that to say is, please do some of worksheet 5 so that tomorrow goes easier.